Hello everyone. Today we are going to see the definition of subspace. In the last lecture we have seen definition of vector space. So if you have not seen that video, I recommend you that you first see that video and then come here back to this video. A non-empty subset W of a vector space V, remember it should be non-empty subset W of a vector space V is said to be a subspace of V. Note why it is called as subspace, because it should be a vector space itself under operations as in V. So actually subspace means it is a vector space only, therefore we are having this space word. It should be a vector space only, but it should be what? A subset of a vector space. So in other words, you can say a non-empty subset of a vector space is said to be a subspace if it itself is what? A vector space. So we will see few examples on it. So let us go for the first example. V is equal to R2 is there. You know how does our R2 look like? R2 is equal to set of all x comma y such that this xy belongs to what? R. This is our R2. Now just observe carefully. What is the difference between this R2 and W? Okay, you can easily see actually this W is nothing but it is a line y is equal to x. So it is a line passing through origin, okay, somewhat like this. Okay, this is our W, and this W is actually a subspace of what? R2. So in order to show W is a subspace of R2, we need to show that it is non-empty first of all, and then it itself is a vector space under the operations in V. What do you mean by under operations in V? Means same addition as well as scalar multiplication as in V. So in this case, this W is a subspace of R2 with respect to usual addition and scalar multiplication in R2 that we have already seen in last class. Now, in order to show that this W is a subspace, we are first of all supposed to show that W is non-empty. That you can easily see because there are infinitely many elements in W, so you can take any element. So I will take it to be what? 0 0. So here 0 0 belongs to W, and therefore W is non-empty. Then we are supposed to show W is itself a vector space. So in order to show this, we are supposed to verify that 8 properties that we have seen in last class. But you already know that in order to verify these 8 properties, lot of time will be required. So therefore there is a subspace criteria that is called as necessary and sufficient condition that we will see later on. Now in the second example, this singleton 0, remember it is a bold 0. This singleton 0 and V are always subspaces of a vector space V. Means whatever examples of vector spaces you know corresponding to each vector space, we are always going to have two subspaces. They are called as improper subspaces. For example, for R2, our two improper subspaces will be, remember what is 0 of R2? It is 0 comma 0, Okay, it is corresponding to this. So it is 1 and the other one is R2 itself. So these are two improper subspaces of R2. So this is going to happen for the any vector space V. Now note one, intersection of subspaces is always going to be a subspace. So if you have a vector space V, suppose, and you are having some subspaces of vector space V, I will call them as W1, W2 and so on. So the intersection of this W1, W2 and so on is also going to be a subspace of V. This is the meaning of intersection of subspaces is always a subspace. Next, union of two subspaces is a subspace if and only if one is contained in the other. The meaning is, if you are having a vector space V and suppose this W1 and W2 are subspaces of V, just a minute, yes, okay, suppose you are having a vector space V and W1 and W2 are subspaces of V, then this W1, the union W2 will be a subspace of V if and only if one is contained in the other, means either W1 should be a subset of W2 or W2 should be a subset of W1. Okay, so this is the meaning of second note. Now the third note is, if W1 and W2 are subspaces of V, then their sum, that is W1 plus W2, is also a subspace of V. Now what is W1 plus W2? Simply you take one element of W1 and one element of W2 and add them. So you will get an element of W1 plus W2. So all such combinations, element of W1 plus element of W2, will give you the elements of W1 plus W2. So sum of the vector spaces is always sum of subspaces is always what? A subspace. Now we will go for the necessary and sufficient condition. So it says that, so now we will go for necessary and sufficient condition for a non-empty set to be a subspace. Why we are going for this necessary and sufficient condition? Because as seen in the previous definition, W is said to be a subspace if it is non-empty, obviously, it is a subset of V and it itself should be a vector space. But in order to show it itself is a vector space, we need to verify that 8 properties, which is very lengthy job. So therefore we will reduce that to simply what? 2 properties in this necessary and sufficient condition. So now this statement says, in order to show that W is a subspace of vector space V, we are supposed to show W is non-empty, which is important. The second thing is W is subset of V, and then these 2 conditions. The first condition is called as W should be closed under addition, and the second one is W should be closed under scalar multiplication. Now what is the first property saying? You take any 2 elements of W and show that their sum is also in W. And what is the second property saying? You take one element of R, I am calling it as alpha. You take any element of W, I am calling it as U. Remember, this alpha is also arbitrary, and show that this alpha U belongs to what? W. Take alpha from R, U from W, and show that alpha U is in W. So if you are able to show this two conditions in addition to these two statements, then we will say that our W is what? A subspace of a vector space V. Let us explore this with the help of an example. So over here we are supposed to show W is a subspace of V. So the first thing is we are supposed to show it is non-empty. Now remember, in order to show subspace is a non-empty, the easiest way is to show the zero vector lies in W. Now try to understand how W is defined. W is a collection of elements of R3 such that the sum of the coordinates is equal to 0. For example, if you think of this point 111, this 111 does not lie in W because what is the sum of the coordinates? It is 3. Now if I take another element, suppose 1 minus 1 and 0 suppose. Now if you add these 3 coordinates, you will get 0. So therefore this element lies in what? W. Okay. So in this way your set W is given to us. Now let us show W is non-empty. Now you can easily say that the element, that is 0 vector, clearly our 0 vector, that is 0, 0, 0 belongs to what? W. Why? Because see, what is the sum of the coordinates? It is 0. So therefore this W is non-empty. Okay. Subset, there is no issue with the subset. Clearly W is a subset of what? R3, or that is nothing but V. Now let us verify these two properties. The first property, so I will need two elements of W. Now observe, how do elements of W look like? They are the coordinates of the type x, y, z such that the sum of the coordinates is equal to 0. So I will say let this x, y, z, comma x1, y1, z1 belonging to W be any elements. Okay. Yes. Okay. So as these are elements of W, so therefore what will be the sum of the coordinates of x, y, z? Therefore this x plus y plus z will be equal to 0, and this x1 plus y1 plus z1 will be also equal to 0. We'll call it as sum 1. Okay. Now what we have to show is, we have to show that the sum of x, y, z and x1, y1, z1 belongs to W. That is to show this x, y, z plus x1, y1, z1 belongs to W. That is nothing but what? If you add this, you will get x plus x1 comma y plus y1 comma z plus z1. So we have to show this element belongs to W. When this element will be present in W, that is nothing but what? If the sum of the coordinates is equal to 0, that is x plus x1 plus y plus y1 plus z plus z1 is equal to what? 0. So simple, I will start with LHS and I will show that it is equal to RHS. Okay, so I will say consider LHS. That is x plus x1 plus y plus y1 plus z plus z1, which is equal to which can be written as x plus y plus z by simply rearranging the terms, plus x1 plus y1 plus z1, which is equal to what? Now this x plus y plus z is already 0, plus this is also 0, that is from this 1, okay, and therefore it is equal to what? 0, and therefore we can say the sum xyz plus this x1 y1 z1 belongs to what? W. Now we will go for the second condition. So for second condition we need one element of R, so I'll say let alpha belongs to R, and one element of W, I will call it as X, Y, Z belongs to W be any elements. Now what I have to show here? I have to show that this alpha multiplied by X, Y, Z belongs to W. That is nothing but what? If you put this alpha inside, that is alpha X comma alpha Y comma alpha Z belongs to W. But when this element will be in W? If the sum of the coordinates is equal to 0, that is alpha X plus alpha Y plus alpha Z is equal to 0. Also note one thing, I will write it here. Now since this xyz is an element of W, so therefore the sum of the coordinates is going to be 0. I will call it as Roman 2. So in order to prove it, I will simply consider LHS, that is alpha X plus alpha Y plus alpha Z, which can be written as, if you take that alpha out, so X plus Y plus Z, but value of this is 0 from that 2, so alpha dot 0, and you know this is nothing but 0. So that is our RHS. Therefore you can say that alpha into this X, Y, Z belongs to W. That is what we wanted to show. Therefore we will say that this W is a subspace of R3, and that is what we wanted to prove. So you can explore some more examples from our first year notebook. So thank you.